Good afternoon. I'm Dr. Richardson, and this is lecture 4 of the course, Using Vector Calculus to Solve Problems in Electricity and Magnetism. My email address is srichard22@comcast.net. And again, to review organizational procedures for the course, learning is not a passive activity, so you have to take notes. You won't get anything by sitting back and watching me write on a whiteboard. You need to take the notes in real time as we're going through discussions and derivations. Problem sets are given in this course as we speak on the Google Drive. Problem set 1, problem set 2, and problem set 3 are posted, as well as their solutions. I will have problem set 4 available online at the Google Drive site by Monday at the latest. And the solution key for problem set 4 will be available a week after that. So you need about a week's time to do the problem sets. You should do the problem sets individually by yourself. That way you'll get the maximum from this course. If you don't do the problem sets, you're not going to get anything from the course. Please do them independently without consulting any live people or online sources. You need a ruler if you don't have one already. And I encourage you to ask questions. So after the lecture today ends at 3:30, we have a recitation section which goes at least to 4 and longer possible if needed, which will be available to answer questions online about the course material, lectures, or problem sets. And again, you can always send me an email message at the above email address anytime, in weekends included, and I promise to get back to you within 24 hours. Okay, so let us start from reviewing something we talked about last lecture and lecture 3. We were looking at surface integrals. And we were going through an example of how to evaluate them. So we denoted a surface integral with the capital letter S under the integral sign, and it typically involves vectors in the integrand. In this case, the dot product. This is an example of a surface integral. The dot product of two vectors, v and ds, the differential surface element. So the S means that you're doing a surface integral. And I should say something that I didn't emphasize last time. Here, this integral is over an open surface, as opposed to an example that you could do where the surface integral is done over a surface that's closed. And that's what the circle through the integral means. So we looked at an example last time of how to evaluate a surface integral. We haven't really discussed what it means, and I'm going to put that off to later in the course, but I will say, just to whet your appetite, that surface integrals of this form are also defined as being the flux. Flux has something to do with flow of something through something. We'll come back to this idea in much more detail later. Okay, so let's return to the example we were talking about last time. We're looking at a box or cube in three-dimensional Cartesian coordinates. So again, it's my x, y, and z. And my cube has 6 sides to it. I don't know where 7 came from. The cube certainly has 6 sides. So I'll draw them in. And I want to give these sides numbers. So in fact, S1 will be the front part of the cube. S2 will be the back. S3 will be the right-hand side of the cube. S4 will be the left-hand side. S5 will be the right-hand side. And there's a bottom to this cube, S6, but in this problem, I'm not worried about that. So each one of these sides has a unit normal vector. So it's clear that here are the unit normal vectors for the front and back. For the left-hand side, here's the unit normal vector. Actually, in my convention, that'll be the unit normal vector for the right-hand side, and the unit normal vector for the left-hand side will be 4. And in this problem, I'm only going to consider the top. So it's defined by a unit normal vector that points upwards. And again, you know, don't forget our unit vectors. They tell us exactly what's going on. So again, in this problem, we were worried about calculating the flux, since I've introduced that word, of the vector v through 5 sides of a cube. And in this problem, the vector field, or vector, excuse me, was 2xz. I'll define what I mean by vector fields later in this lecture, plus x plus 2y hat, plus y times z squared minus 3k hat. And ds1 is the differential surface element for side 1. That turns out to be I hat dy dz, as we discussed last time. It's also shown in great detail in problem set 3. And S2, or ds2, the differential surface element along surface 2, is minus I hat dy dz. So in fact, I'm not going to repeat this, but we evaluated at least 2 of the 5 surface integrals in last lecture. ds1 over ds1 s1 turns out to be a number, 16. And we also showed that the surface integral of v over surface 2, or the flux of v over surface 2, this is up on top, I have the flux of v through surface 1. The flux of v over surface 2, we actually evaluated last time also, and it turned out to be 0. So what I want to do is continue with this problem. I've already tackled surface 1, surface 2. I need to do S3, the right-hand side of the cube, S4, the left-hand side of the cube, and S5, the top. Sorry, that's a typo. The top of the cube. So again, the cube has 6 sides to it. And I'm only in this problem worried about calculating the surface integral over 5 of the 6 sides. So I'm going to keep my figure here. And get rid of the work that we did last time. And now I need to evaluate the surface integral of v over side S sub 3, or the flux of v through S sub 3. So I'll need a couple of things. I certainly will need to know v. So I'll remind you what it is again. 2xz I hat plus x plus 2j hat plus y times z squared minus 3k hat. And then the second thing I need to know is what is ds over surface 3. So if you look at this diagram, it follows that that's just j hat dx dy. And the other thing about this surface integral that you'll need to know is that y for surface 3, y is 2. So dy is 0. So you will need to evaluate the integrand inside this surface integral. That's v dot ds. Because y is 2 and dy is 0, this simplifies to, in fact, two terms, x dx dz plus 2 dx dz. So you're really all set. The flux of v over ds over surface 3 is just going to be, it's going to reduce to an integral over x from 0 to 2 of x plus 2 dx. I'm skipping a few steps here that you can fill out, plus or times another integral from over z, where z goes from 0 to 2. So again, the neat thing is that x and z become independent variables. What is a integral over an area, a two-dimensional integral, now just becomes a problem of evaluating two one-dimensional integrals. And I'll leave this for you to do. This is just 12. Okay. So 3 down, 2 to go. So I'll keep my figure. All this work pertains to doing the surface integral over surface 3, or calculating or evaluating the flux of V over surface 3. So now I have to do my third surface integral, and this time it's over surface 4. So same story. Again, what's V? V never changes. It's 2xz I hat plus x plus 2j hat plus y times z squared minus 3j hat. So V never changes in any of these surface integrals. Over surface 4, the differential surface element is minus j hat dx dz. Again, make sure you understand these differential surface elements, where they come from, why they are what they are, and there's ample practice for this in problem set 3. So along surface 4, turns out that y is 0. That means that dy is 0. So all you have to do is take the dot product of the vector v with the differential surface element ds along surface 4, and that turns out to be minus x plus 2 dx dz, and now you're good to go. The surface integral of v over S4, or the flux of v over S4, is going to simplify into evaluating two integrals. One integral is going to be integral over z, and the other integral is going to be integral over x. Again, x and z are independent variables. So this two-dimensional integral breaks up into two separate, distinct one-dimensional integrals, which you can do, and you can evaluate this guy, and she is minus 12. 4 down, 1 more to go. Okay, and again, make sure you follow all these steps and you understand what's going on. The key thing is, remember what the vector that you're integrating over is. Remember how to calculate the differential surface element. Look at that differential surface element and see if it tells you anything special. In this case, it does. Y is 0, so dy is 0. Evaluate the dot product of b with ds. Plug it in. That's the integrand of the surface integral. And then evaluate it over the independent variables. In this case, they are x and z. And again, hopefully you can see why I picked the convention that I take z, put a horizontal bar in through it, so that I don't confuse that with the number 2. Okay, our final surface integral to do is the integral over the top of the cube. Again, I'm not going to worry about the integral over the bottom of the cube. So this problem does not involve calculating the flux over a closed surface. We'll have ample examples of that later in this course. So this is my last chore to do. But the method is still the same. The method is identical to all. Okay, so again, I don't have any problems with, again, reminding the audience what V is. It's a vector 2xz I hat plus x plus 2j hat plus y z squared minus 3k hat. The next thing I need to do is figure out what the differential surface element is along S3, S5. And by inspection, that's a vector that points in a positive k hat direction, and it has a magnitude of the product of dx and dy. So I need to take the dot product of these two creatures, v dot ds, and that will give me y times z squared minus 3 dx dy, just using the product, the property of the dot product of vectors, in particular the dot product of unit vectors. So I'm almost finished. I have to do the surface integral over S5 of v dot ds, or calculate the flux of v through S5. That's going to break down to 2 integrals, but let me be a little bit more careful here. Namely, if I look at S5, I see that z has to be equal to the number 2. dz is 0, but z is 2. So now I'm in a position to calculate this, the flux of v over surface 5. And that's simply just the integral over y from 0 to 2 times the integral over x from 0 to 2. Once I've done some arithmetic, I've gotten rid of the z here by recognizing it's just z squared, or 4. So finally, you can evaluate this integral, and he is 4. Okay, so we've developed some expertise in calculating surface integrals. Why we want to use these guys, we'll talk about later. So the last type of integral I want to go over is a volume integral. So you can imagine a volume integral of a vector. Let's call that vector something else. let's call it F. So if you can resolve F into its components, and let's say F can be expressed in terms of Cartesian coordinates, then my volume integral simply reduces to doing 4 individual integrals. And then remember, the unit vectors are just constants. So they come out. And so for this case, what was a big headache, namely evaluating a integral, a volume integral involving a vector, reduces to evaluating 3 ordinary scalar integrals. Scalars, this is a lesson we should learn and always repeat. Scalars are always easier to deal with than vectors. So if you have a choice of doing a problem using vectors, you're going to have to do a lot of work. If you can resolve the problem so it's just a problem of scalars, that's a much easier thing to do. So I'm going to do a problem where I want to calculate the volume integral of something called a scalar field or scalar function. So that sounds scary, but it's really not. Let's see what I'm talking about. So here's a function t. It depends on 3 independent variables, x, y, and z. And its function is just y, x times y squared. So one example of this scalar field, a scalar function, it's the density of a substance at some point. Piece of gold, piece of platinum, an alloy, a copper platinum alloy. At every point in the material, x, y, z, there's a density that you can calculate doing this relationship. So I want to calculate the volume integral of the scalar function over a prism. So this really is a volume integral. So what does my prism look like? And again, I'm going to do this problem in 3-dimensional Cartesian coordinates. So let me carefully sketch in this prism. Okay. Now, here at this point, x will be 1. So this is how I'm defining this prism. At this point, y will be 1. And at this point, z will be 3. And again, let's not forget our ubiquitous set of unit vectors in 3-dimensional Cartesian coordinates. So I want to do this integral. This is the problem I want to solve. This is a volume integral. So that's what the v under the integrand means. So this is a volume integral. But unlike the previous case, it's a little easier to do because the integrand doesn't involve a vector, it involves a scalar, which is nice. So one thing at a time. First thing I'm going to do is going to figure out, well, what is, I know what t is, right? It's just a function of x, y, z, or x times y squared. What's the differential volume element? Well, it would make sense to do this problem in Cartesian coordinates. You might try to do it in cylindrical polar coordinates, and you might try to do it in spherical polar coordinates. You certainly can't do it in plane polar coordinates, and that's going to be a lot more work. Okay, so let's start forward. And again, for illustration's sake, on this slide, let's repeat the picture of the prism. I probably should have put in my coordinates first, but that's okay. It's x, y, z, where this point is x equals 1. So my prism intercepts the x-axis at x equals 1, intercepts the y-axis at y equals 1, and it intercepts the z-axis at z equals 3. So to evaluate this volume integral, I need to put in t, that's just x, y squared. And actually, I misspoke. T is actually going to be x times y squared, z squared. So for this particular problem, t is that, and actually t is x times y times z squared. Sorry. Okay. I can make this anything way I want, but for this problem, the way I've set it up, that's the way I want to go. So let's go back to here. So t is my scalar function. Scalar field depends on x, y, z squared. And I know I have to calculate dv, but in three-dimensional Cartesian coordinates, that's simply just dx, dy, dz. So this problem is a little trickier to do than an ordinary three-dimensional integral. And the reason why it's trickier is you have to realize that x and y, these two variables, are not independent. So you have to be careful. Namely, if you take this figure and plot from it, or draw out from it, the xy plane, you will see that the edge of the prism defines a line. This is always a right triangle. The equation of this line is just 1 minus x. So it has a slope of -1. So x and y are related. They're not independent. Now I could flip that two-dimensional figure around and get a similar plot. In this case, I'll choose this to be x and this is y. So in this case, x is just 1 minus y. But both of these things say the same thing. So x and y are coupled or related. So when you go back to the problem at hand of trying to evaluate this three-dimensional integral, you're going to have to do it very carefully. So what am I talking about? Let's take that into account over here. Let's take the easy guy first. Z is just a variable that's just going to go from 0 to 3, the height of the prism. So that's easy. Y is going to go from 0 to 1. That's going to involve a prism. X, however, goes from 0 to 1 minus y, as we saw over here. So these are the limits of integration for this problem. So it would behoove you to do the integral over x first. Okay, in previous examples, you know, if the variables were independent, then it didn't matter which order you did the integration. But here it's probably going to make a lot more sense to do the integral over x first, then you'll do the integral over y, then you'll do the integral over c. So let's see how this works. So here's the volume integral you want to do. It's x times y times z squared of dx, dy, dz. And that's going to be an integral over z, where z goes from 0 to 3. So I don't mind writing that in there. It's going to be an integral over y, where y goes from 0 to 1. And there's going to be an inner integral I'm going to do over x, where x goes from 0 to 1 minus y. There's only one part of this creature that depends, only one part of the integrand that depends upon x, so there it is. So I evaluate this guy, but note that this is going to be a function of y. This is not going to be a number. But that's okay, because once I get it, then I have to do my second integral over y. And that's going to be y. Let's do all this in the same color scheme. Y dy. So that's the second out of third integrals. Then I'll get a number. And then finally, I will do my final integral, which is z squared over dz. So you do the integral over x first, you'll get an answer that will depend upon y. Then you'll do the integral over y, just using the elementary rules of integration of functions of a single variable. Then finally, you'll get a result, or you'll get a function that just depends upon z, and then you can integrate over z. And I'll leave this as an important practice problem for you to work out. It is 3/8 over 8. Okay, so line integrals and surface integrals we have looked at. We in principle know how to do them. And there's lots of practice in doing these guys in problem set 3, both in Cartesian coordinates and in cylindrical polar coordinates and spherical polar coordinates. So this is one of the reasons why we went through the drill of learning how to set up these various coordinate systems, because we're going to do integrals in electrostatics that are not just in symmetry dictates that you should not look at them just as integrals in Cartesian coordinates. You could in principle, but they're going to be a bear to do. They're much easier to do them in cylindrical polar coordinates or plane polar coordinates or even spherical polar coordinates. Okay, so this gets us to today's topic, the idea of vector operators, that vectors can be viewed as operators. So I need to do a review of some things to sneak up on this. So remember what you know about functions of a single variable from elementary calculus. What is a function? A function is a box. That's all it is. That has input and output. So the input would be x. You put it inside your box or function, And what that function does is acts on the input according to some rule and gives you an answer. Let's say y. So for example, here's a function. The exponential function. It looks like this. Clearly, when x equals 0, y is 1. And x, again, is input, gives you output. Sometimes x is called the domain, and the function y, the result, is called the range. So there are a lot of interesting things you can do with functions. One thing you can do is take their derivatives. And in this case, I'm talking about functions of a single variable. I'll talk about functions of several variables in a minute. So to do that, what you do is you take your function y, you evaluate it at a point x, and a point slightly to the left or right of x, delta x. You subtract from that the value of the function at x, and you divide that by that small shift delta x. And this almost looks like a slope, but it's really just a quotient. It's got something in the numerator and something in the denominator. And Newton probably wrote it down for the first time. It's called a Newton quotient. Now, if you take the limit as delta x gets smaller and smaller, then you get the derivative of the function with respect to x, or another way of writing that is just f prime. And what is this guy? It is simply the slope of your curve or graph at some point. Okay? So for example, if we go back to that exponential function and we looked at, again, this is all a review. At any point, you can evaluate the derivative of the function with respect to x. That's very easy for the exponential function. And physically, all that is the slope of that curve at this particular point. Okay. Now, this is fun. And again, you know how to do these derivatives. I mean, when you calculate the derivative of a function, you don't go and do it this way. You don't evaluate the Newton quotient and then take the limit. I mean, numerically, you could do that, but if you do it analytically, that's not how you do it. But what bails you out is you spend a lot of time in elementary calculus studying rules to take derivatives of a set of functions. And here are some of them, as well as powers of n. So these guys, you know, they obey very nice, simple rules that allow you to avoid actually writing down a Newton quotient and taking its limit. So what about functions of several variables? And why you would have to worry about functions of several variables, we'll see in a minute. So let's make our life simple and pick a problem where the function just depends upon two independent variables, x and y. Well, you can also write down an expression for the derivative of this guy, but you have to be careful because you have two independent variables you're worried about. So you have to treat, when you write down your Newton quotient, you have to treat one variable or each variable one at a time. So in fact, if you took in your numerator the function at x plus delta x comma y and subtracted from it the value of the function at x or y, and you divided by delta x, and then you took the limit of this Newton quotient as delta x goes to 0, you would not get a total derivative, you'd get a partial derivative. Excuse me. And that's what this notation tells you. This is a partial derivative. And what it tells you to do is take your function, fix the variable x, y, treat it as a constant, and then take the derivative of the expression with respect to x. So that's why it's called a partial derivative. Now, x is not the only variable in town. There's y. So you could write down a Newton quotient for it, changes in y. And again, the numerator is going to be different. And clearly the denominator is different. And this guy is a partial derivative of your function f with respect to y, holding x fixed. Okay. So all you'd have to do is write down this Newton quotient, take the limit, in this case, in case 2, as delta x goes to 0, and in case 1, as case 2, delta x goes to 0, and case 1 as case 2, delta y goes to 0, in case 1 as delta x goes to 0. So that's in principle how you'd calculate a partial derivative. You may be smarter than I am. I can't see this immediately. So what I would do is just look at an example and see how this works. And in the example, you don't literally have to sit down and write down these Newton quotients. So example 4, this is lecture 4, example 4.1. Here's a function of two independent variables, x and y. 2x cubed plus 6xy plus y squared. So I want to evaluate the partial derivative of f with respect to x and fix y. So that means that I have 3 terms here, 1, 2, and 3. If I look at the first term and treat y as a constant, y is not there, so that's easy. So I just take the derivative with respect to x using the rules of elementary calculus. So that's just 6x squared. The second term, number 2, to take the partial derivative of this guy, f, with respect to x, I treat y as a constant. I treat y as a constant, and I just take the derivative with respect to x, and that's just 6y. And the final third term is easy to evaluate because y is a constant. So when I take the derivative of that third term with respect to x, I get nothing. And you should convince yourself that the partial derivative of f with respect to y, holding x fixed, again, is just 6x plus 2y. Now, I will say this now and use this later. Sometimes this notation is cumbersome. So another way to write the partial of f with respect to x holding y fixed is just this 1 partial x sub x f. And similarly, the partial derivative of f with respect to y holding x fixed is just a partial sub y of f. I mentioned that because you may see that notation or approach in other courses. We may do that eventually, but when you first look at this business, it's useful to spell the whole thing out so that you can see what derivatives you're taking, what variables you're taking the derivative with respect to, and what variables you're holding fixed. Okay, so a reasonable question to ask is, how do you plot a function of many variables? Variations, but variables. So, for a function of a single variable, the plot of this function is just a graph. And we looked at a simple case, namely the exponential function. So when you plot a function, you just write down its graph, provided that that function is a function of one independent variable. Now, suppose you have a function of two independent variables, x and y. Well, what this says is that you tell me what x and y are. That's my input. You put it inside a box, which is my function. And out comes output, which will be a number z. So for those of you who are familiar with complex variables, z is typically the symbol you use for complex variables. So there's a possibility of a confusion here, but I can eliminate that confusion by just simply saying that z is just a number, it's just complex. So in fact, here are some examples of functions of several variables. This is really an elliptic paraboloid. If you don't know what that is, that's fine. Way to problem set 4. And here's an equation of a function of 3 independent variables. But you know what this is. This is just the surface of a sphere, where A is a constant. Now, I've made a conscious decision here that I'm not going to attempt to try to draw these or plot these functions of several variables on the whiteboard. What I am going to do, and I leave it to problem set 4, which should be available on Monday, is assign to you the free piece of software, Wolfram Alpha. And this will allow you to plot functions of several variables, let's say a function of 2 variables. And for the case of a function of a single variable, you get a graph. For functions of 2 independent variables, you get a surface. So you can take my word for the moment, or you may not take my word for the moment that that's a true statement. But in problem set 4, you will be given lots of opportunity to plot various surfaces given the functions using this wonderful graphics tool, Wolfram Alpha. Okay, so back to my functions of several variables. I know how to plot them in principle. I know how to take partial derivatives of functions of several variables. And the question is, what do these partial derivatives mean? Okay, it's very interesting and it's very important to be able to calculate these guys. But I'd like to come up with a nice physical understanding of what to do with these things. What do they mean? So again, I always go back to this theme of if you're faced with some complicated expression or idea, start with something you know first. So let's start with a discussion of a function of a single variable, where x is my input, function is my box, and my output is y. So the derivative of this function is just df dx times dx. The differentials, dx in the numerator and dx in the denominator, you can treat them as if they're numbers and they cancel to give you what's on the left-hand side. This thing df dx has a nice important physical meaning for functions of a single variable. It's the slope of the graph f of x. So here's an example of two functions. Here's x, and here's f of x. And it's clear here at every point along this function that there is a slope that you can calculate by just taking this total derivative, and the slope at each one of these points is pretty small. Contrast that to another example. Another function. It's a completely different function, so let's call it g. And let's say that function looks like that. And at every point along this function, the slope, the total derivative of g with respect to x is quite large, and it gets larger and larger as you get away from the origin. So all this is true if you have a function of a single variable. What happens if you have a function of several variables? So let's take an example. Let's have a function which we'll call t, and it'll depend upon x, y, and z. And in this case, t is temperature. So this has a nice, very simple physical meaning. This is an example, again, of a scalar field or scalar function. Both terms are synonymous. And what this creature does, well, you can either call this a scalar field or a scalar function. Both terms are equivalent. It tells you the temperature in a room at a point x, y, and z. So the question you'd like to ask as far as derivatives are concerned is how fast, you saw this for a function of a single variable, it tells you how fast the curve changes. Well, for a function of three variables here, how fast does the temperature change? So that's the question. The answer is kind of complicated. It depends. Depends on the direction that you're going. And it might seem that you need an infinite number of answers to determine this problem, because it's going to depend on whether you go from the left-hand side of the room to the right-hand side of the room, or up or down, or whatever. But that's not going to be the case. So the temperature of the room depends upon X, Y, and Z. The derivative of the temperature in the room can be written out using the laws of partial differentiation. Namely, it's the partial derivative of t with respect to x dx plus the partial derivative of t with respect to y dy. Remember, t here is temperature, it's temperature in the room, plus the partial derivative of t with respect to z dz. Now you see that in all these partial derivatives, I have to hold the other variables fixed. That gets to be a pain to write it down explicitly. And it's even worse if you've got 5, 6, or 30 variables. So now you can see why most folks don't bother to put in these subscripts, because it's assumed that when you write down a partial derivative, it means that you're holding the other variables fixed. So this tells you the change in the temperature in the room. But this guy looks very familiar, possibly. Namely, it almost looks like a dot product. So what do I mean? When you take the dot product of two vectors A and B, you get A sub x times B sub x plus A sub y times B sub y plus A sub z times B sub z. So this equation here, especially the right-hand side, looks almost like a dot product. The question is it a dot product of what? Or what is it a dot product of? So let me get rid of these guys. I've introduced this concept, I've used it, so I can discard it. Well, I'm going to break it up into two vectors. The first vector I'm going to call I hat partial of t with respect to x plus j hat partial of t with respect to y plus j hat partial of t with respect to z. Now I've got to dot this thing into another vector, because after all, when I take the dot product of two vectors, I must get a scalar. dt is just a change in temperature of the room, that's a scalar. So the thing that has to go over here is just I hat dx plus j hat dy. We've seen this creature before. Plus k hat dz. Excuse me. So let me introduce some simplifying notation. I'm going to call this creature inside the square box del t. And I'm going to dot this into this thing over here, but that's just simply the differential vector dr. So whatever this thing here is, it has to be a vector. This is certainly a vector. And when you take the dot product of two vectors, you get a scalar. So all is right. Okay. Now I have to do some more thinking. What is this thing? And what is this symbol here? So I will define a symbol called del. And this thing is simply I hat partial with respect to x plus j hat partial with respect to y plus k hat partial with respect to z. This is a operator. It's a vector operator. Because what it does is it looks for things to take partial derivatives of. When I take del, which is a vector, and act on the temperature, which is a scalar, I get I hat partial derivative with respect to x of t plus j hat partial derivative of t with respect to y plus j hat partial of t with respect to z. And again, everything here on the right-hand side, by definition, has to be a vector. So another definition, del acting on t. T is a scalar function. Del is a vector operator. When you act on when you take del, which is a vector, and act on a scalar function, you get a vector function. This thing has another name called the gradient of the scalar function t. Those are too many words, so let's just abbreviate this as grad t. So let's say that again. When you take the gradient of a scalar function, you get a vector. So you can only take the gradient of a scalar. Let's say that again. So t is a scalar function. When you act on it with the vector operator del, you must get a vector. And another way to write del acting on t is taking the gradient of t. Okay, couple things to do here. First question is, let's look at an example of calculating the gradient of a scalar field or function. That'll be example 4.2. And then the next question we'll ask is, does this gradient of a scalar function mean anything? So what does this mean? So first things first, let's do example 4.2. Let us take a function. Let's say that the temperature of a room at any point x, y, z has this behavior, x squared plus y squared minus z squared. And so let us find, in this example, the gradient of t. That means I have to take del and act on t. That means I have to get a vector, and that vector has 3 components. And here they are. So I know what t is. I have to evaluate, in order to get the gradient of t, I need to calculate the partial derivative of t with respect to x, multiply that by I hat, take the partial derivative of t with respect to y, multiply that by j hat, and then take the partial derivative of t with respect to z, and multiply that by k hat. So let's just do that. This is just using the rules of partial differentiation. So again, t, I'll write this again, it's x squared plus y squared minus z. The gradient of t is just del times t. Both these terms mean the same thing. So the first term is just the partial derivative of t with respect to x. Second term is the partial derivative of t with respect to y. Third and final term is the partial derivative of t with respect to z. I know how to evaluate these partial derivatives. You know how to do it. And you should convince yourself the answer is 2x I hat plus 2y j hat minus k hat. So the gradient of a scalar function is a vector. And another way to write this is the gradient of t is just 2x I hat plus 2y j hat minus k hat. So that's the easy part. The hard part is, what does this thing mean? Or the challenging part is, what does this mean? And it actually has a very nice physical interpretation. Namely, let's go back to our expression. The change in the temperature of the room is just the gradient of the temperature dotted into a differential vector, dr. I know how to take the dot product of vectors, and in particular, in this case, it's just the norm, magnitude, or length of the gradient of t times the magnitude of dr times the cosine of the angle between them. So if you were to fix dr and vary theta, it's easy to see that dt has a maximum value. What is that maximum value? That maximum value occurs when the gradient of t and dr are both in the same direction. Why? Well, this expression here at the top says that the change in temperature is going to depend upon the dot product of these two vectors. If I take the dot product of these two vectors, I get a scalar. And this quantity is going to depend primarily for fixed dr on the value of theta. This has a maximum value when theta is 0, namely when delta t and dr are in the same direction. And so this tells you the meaning of the gradient. The change in temperature of the room is maximum when theta is 0 or the gradient of t is in the same direction. So I'm just writing this again. As dr, and the key point here is that the gradient of t is a vector that points in the maximum increase of temperature. Okay. So let's look at a physical example to see how this works. So I have my room, and I have a temperature every point in the room given by this scalar function. So the temperature of the room is not constant, depends on where you're at. So suppose I have a mosquito. In the room, and suppose the mosquito is located at the point x equals 1, y equals 1, z equals 2. And suppose this mosquito wants to fly in such a direction to get as warm as possible. That's a reasonable thing for an insect to do. So in what direction must it fly? Well, it's a very simple answer. The gradient of t, which is something we calculated, is a vector that points in the direction where the temperature increases the most. But again, my mosquito is initially at the point 1, 1, 2 in the room. So I have to evaluate this vector at that point. That tells me where my mosquito starts. And the answer is my mosquito has to fly in the direction of this vector, 2i hat plus 2j hat minus k hat. So the gradient of a scalar function is very special. It's not just a vector. It's a vector that points in the direction of the maximum increase of the vector function, of the scalar function, t. In this case, it's temperature. So I am going to leave to you problem set 4 for lots of practice with calculating gradients of scalar functions. That's pretty straightforward to do. That's just using partial differentiation. And also some another example of a physical interpretation of the gradient of a scalar function, specifically with regard to surfaces. Okay, so it's not going to be good enough just to be able to calculate these guys. You need to know what you're calculating. Okay, so problem set 4, which will be available on Monday, is critical. So I've talked about scalar fields when using the gradient operator. I now have to talk about vector fields. So what is a vector field? So suppose somebody gives you a point. Let's say you're in 3 dimensions, x, y, z. And at that point, you're not going to assign another scalar value. So it's not going to be a scalar field. You're going to assign a vector, v, let's say. So here's an example of a vector field. The vector field v has components 6xy. This component points in the I hat direction, and it has another component to 7x squared y that points in the j hat direction. So what the vector field does is that you give me a point x, y, and at that point you give me a vector. So let's bring all this together. You can operate on a scalar field with the operator del. When you do that, that's called taking the gradient of that scalar field. Similarly, you can ask the question, what happens if you operate not on a scalar field, but on a vector field with the vector operator del? Well, in this case, what you're doing is taking the dot product of del with a vector field v. And this thing has a name. It's called the divergence of that vector field. So this is something that you can write down and calculate in principle. remember, so this, how do you calculate the divergence of a vector field? Well, first things first, remember del, he is a vector operator, I hat, partial of something with respect to x, j hat, partial of something with respect to y, k hat, partial of something with respect to z. Del is my vector operator, and it's looking for something to act on. That's why I call it a operator. It's a vector operator. V is a vector. It has components. And so for this example, 6yx I hat plus 7x squared y j hat. So if I want to calculate the divergence of the vector field V, that's the same thing as taking del and taking its dot product with V, which is, I could write this whole thing out. Here's del, my vector operator. So this thing in square brackets is a vector, and I'm going to dot that into the vector V, which is 6xy I hat plus 7x squared y. Now, in principle, I should get 9 terms, right, when I evaluate this dot product. But it turns out, because of the properties of the unit vectors, which we've seen before in Cartesian coordinates, of these 9 terms, 6 of them are going to disappear. So you should be able to convince yourself that in this example, the divergence of V, which is the same thing as del dotted into V, is just going to be 6 at y plus 7x squared, which is a scalar. So if you take the divergence of a vector, you must get a scalar. You don't get a vector, okay? When you take the gradient of a scalar function, you must get a vector. So what I would like to do is summarize what we just said. So the gradient of phi, which is the same thing as del acting on phi. So phi is a scalar field. When you take the gradient of a scalar field, you must get a vector as an answer. When you take the divergence of a vector field, F, that's the same thing as taking the operator del and taking its dot product with F. Note that this does not make any sense, interchanging those vectors, because vector operators act on creatures to the right of them. So you never want to do something like this. The result of this, taking the divergence of a vector field, or taking del and dotting it into F, is that your answer has to be a scalar, a number. Okay. You cannot take the gradient of a vector. That makes no sense at all. And you cannot take the divergence of a scalar. That makes no sense at all. Okay. So I think it's useful to go through a physical example We know how to take the divergence of a vector field. The question is, what does it mean? So I'm going to look at an example, really from elementary fluid dynamics, of a flowing fluid. In this case, the fluid is water in 2 dimensions. I know water flows in 3 dimensions, but I want to get the math so it's simple. So what am I talking about? So here's 2 dimensions. And this is a picture. And along the surface is water that's flowing. So water consists of molecules, mostly water molecules. So in my surface, I have a stream of water molecules, H2O, and they're flowing in some pattern. So I have to tell you what pattern do they flow. And so I'm going to define that by this vector V, which has 2 components, and one of them is going to be 0. So this vector V has a name, hence why I called it V. It's a velocity field, or it's a vector field. It's an example of a vector field. And it tells you how fast the particles are moving in 2 dimensions. So let's see how this works. So along the x-axis, you have 1 and 2, so that's enough. So let's just pick 3 particles, 3 water molecules in the fluid, 2-dimensional fluid. At x equals 1, each one of these water molecules moves in a direction I hat specified by a vector of magnitude 1/2. If you evaluate the velocity field at x equals 1, you get a vector that points in the I hat direction and has a magnitude of 1/2. But there are particles here at x equals 2, and they are moving at a faster rate. Their norms are 3/2. And you get that by just evaluating the velocity field, which is a vector field, at x equal 2. Actually, let's call this 3. So now you'll get 3/2. Okay. So the particles, not all particles move in the same direction or move at the same speed. They all move in the same direction, but as you go further and further to the right, the magnitude of these velocity vectors gets bigger and bigger and bigger. So in this particular model, the 2-dimensional water field, or 2-dimensional fluid, the water molecules are flowing from left to right, but they're moving faster as you go to the right. And you can imagine visualizing this if you go to Rock Creek Park in Washington, D.C., and in a spring day, watching water flow down a river or a small stream. So what does all this have to do with the divergence of a vector field? Well, again, let's go back to our 2-dimensional picture of our water moving. I'm just going to pick 6 molecules of water, of the 10 to the 23rd molecules of water inside the stream. They obey this velocity field. realize that the z component, the y component vanishes, but I just put it in there anyway. And so the question is, what happened? And I could, if I want to, I could actually put in a velocity vector at x equals 2. And the point is that this magnitude is small, this magnitude is larger, and this magnitude is even, so let's say L, and this magnitude, that vector is even larger. So let's construct a mathematical circle. And if you look at this circle, physically, more particles leave the circle on the right as a function of time than enter the circle from the left. If you now take the divergence of this particular velocity field here, which you know how to do mathematically, that's easy, but now for the first time you're asking yourself, what does it mean? You get a result, but that result is positive. And I can interpret this as follows. I need some more space, so I will just get rid of this guy here, and I'll rewrite some of this in a minute. So we said that the divergence of my velocity field was a half. If you let this mathematical circle get smaller and smaller and smaller, what you have is a point. If you just have a circle and you let its radius go to 0, you have a point. And this point is a source of particles. It's no accident that in this particular case, the divergence of V was positive. Now, I'll just say this, and I'll come back to this next lecture. I could have other vector fields or velocity fields. Let's say this one, where I put a minus sign here. And it turns out the divergence of V here is minus a half. And at a point anywhere in this fluid, you have not a source of particles, but a sink of particles. In other words, particles will be getting more and more dense inside that circle. And I'll come back to these examples next time, but I'll just write this out for convenience sake. Finally, here's a vector field or velocity field for the way water flows in 2 dimensions. And it's easy to show. This doesn't make any sense. You have to take the divergence of your vector field or velocity field. Okay, so for this third example, so we've looked at 3 examples, 1, 2, and 3. So my third example, the divergence of V is in fact 0. So I'll give you a hint, and we'll look at this in lecture next time, but you should actually plot this out. In this particular case, all the water molecules are going to be moving at the same speed. And that's what happens when you have a vector field whose divergence vanishes. So it makes a difference whether or not the divergence of a vector field is positive or negative or zero, because that physically tells you something about the field itself. So let's summarize. We've talked about the gradient as an example of a vector operator. The gradient operator is the same thing as del, and it can only act on scalar fields. And it will give, as a result, a vector. So the gradient of a scalar field gives you a vector. You can also take del, so this thing has the name del, and you can act on a vector, E. And you may say, well, is that the electric field? It doesn't have to be, but we'll look at this later. And that is the same thing as the divergence of an electric field. And this creature must always be a scalar. Okay. So in problem set 3, or 4 rather, you'll be asked to do lots of things. You'll be asked to take a series of scalar functions and learn or practice how to take their gradients, as well as taking vector fields and learn how to take their divergence. And you will also go through some problems where you can see what these guys actually mean. So they're not just they're not just mathematical operations. They are vector operations that do things. You can probably guess where we're going next. There's a vector operator or operation involving something called the curl of a vector field. Excuse me, and we'll talk about that next time. Okay, so that concludes lecture 4. In summary, problem sets 1, 2, and 3 are posted on the Google Drive. The solution sets are there. Problem set 4, the solution set will be posted probably no later than Monday, close of business. And lectures 1, 2, and 3 are already recorded in the appropriate site on the Google Drive. This lecture 4 will appear on in the Google Drive probably next Tuesday. Okay, questions, problems, issues, comments. So we have at least half an hour or more for a recitation section, which starts now. Thank you. So questions? Any questions or comments from the audience? So again, problem set 1, problem set 2, problem set 3 are all posted on Google Drive. Their solutions are there also. Problem set 4, it will be available by close of business on Monday. You can start working on that. Lectures 1, 2, and 3 are already available as video clips on the Google Drive. And this lecture, lecture 4, should be available on the Google Drive probably by next Tuesday. Okay, any other questions from the audience? If not, that concludes lecture 4, and see you next week for lecture 5, where we will say a little bit more about the divergence of a vector field, introduce the idea of the curl of a vector field, how you take it, and more importantly, what it means. And then we will have concluded our exercise in building up mathematical tools, vector analysis, coordinate systems and vector calculus, and we can start applying them to the topic at hand, electrostatics. So next time we'll talk about Coulomb's law, what it is, what it means, why it's important, introduce the idea of an electric field, say something about what it means, and then talk about how to actually calculate it using essentially a lot of the tools we've discussed so far. Thanks very much.